The core challenge of HVAC service lies inside sealed copper pipes. Technicians have to diagnose exact thermodynamic changes they cannot physically see. This diagram shows the complete basic refrigeration cycle. It is a continuous, four-stage loop designed specifically to capture heat from indoors and move it outdoors. The system is split precisely down the middle, creating a dedicated high-pressure side and a low-pressure side. The flow through these pressure zones is controlled by four specific physical checkpoints: the compressor, the condenser coil, the metering device, and the evaporator coil. Correctly diagnosing the health of this system requires knowing exactly what physical state the refrigerant is in as it passes through each of these four locations. Standard manifold gauges only measure pressure. They do not tell you the actual temperature of the refrigerant inside the lines. To understand what is happening inside, we have to look at saturation. This is the specific, strict state where refrigerant is actively changing from a liquid to a vapor, or a vapor to a liquid. The physical law governing this cycle dictates that a refrigerant's saturation temperature, its exact boiling or condensing point, changes depending on the pressure inside the system. Once a state change is complete, the refrigerant hits one of two extreme states. It is either superheated, vapor that is hotter than its boiling point, or it is subcooled, liquid that is cooler than its condensing point. Because standard gauges lack the ability to show internal temperature directly, technicians must calculate superheat and subcooling to prove exactly what the refrigerant is doing inside the sealed loop. On the diagram, we isolate the condenser. Its goal is removing heat. Refrigerant enters the top section as a high-pressure, superheated vapor. As the fan pulls ambient air across the fins, the vapor cools until hitting its exact condensing point in the middle. This middle zone is a saturated mixture. As the vapor actively changes state into liquid, the temperature of the refrigerant remains entirely constant. Following the flow to the bottom of the coil, we reach the point where all of the vapor has successfully condensed into liquid. Any further heat removal in this bottom section drops the liquid's temperature below its condensing point. This creates subcooled liquid. Knowing these three geographical zones, desuperheating at the top, saturating in the middle, and subcooling at the bottom, is the only way to conceptualize condenser performance. This table is a pressure temperature chart. It is the mandatory tool needed to convert raw gauge readings into usable internal temperature data. The first step is always identifying the specific refrigerant. Each blend has a different pressure-temperature relationship. If your high side gauge reads a head pressure of 365 psig, you trace that value across the chart to find its matching condensing saturation temperature of 111 degrees. For contrast, a pressure of 118 psig equals a 40 degrees saturation temperature. Guessing internal temperatures without consulting the chart is mathematically impossible. That derived 111 degrees represents the exact, constant temperature of the saturated mixture, hiding right in the middle of the condenser coil. This equation calculates subcooling. It requires subtracting the liquid line temperature from the condensing saturation temperature. We already secured the first variable.
Our PT chart exercise gave us a condensing saturation temperature of 111 degrees. To find the second variable, you must clamp your physical temperature probe directly onto the small copper liquid line leaving the condenser. In this example, the physical line temperature measures 97 degrees. 111 minus 97 yields a final subcooling value of 14 degrees. A healthy subcooling range sits between 8 and 15 degrees. System manufacturers mandate that all TXV systems be charged using this exact subcooling method. Achieving the correct subcooling number is definitive proof the condenser is efficiently removing heat, feeding a solid, unbroken column of liquid to the metering device. Transitioning indoors to the evaporator coil, the system performs the exact thermodynamic opposite of the outdoor condenser unit. The evaporator absorbs heat from warm indoor air, actively boiling low-pressure liquid into a superheated vapor. This formula calculates actual superheat. It requires subtracting the evaporator saturation temperature from the suction line temperature. Reading the low side suction pressure and checking the PT chart gives us the saturation temperature. At 118 psig, that is 40 degrees. Next, measure the actual temperature of the large insulated suction line near the evaporator outlet. Here, it reads 54 degrees. 54 minus 40 results in an actual superheat of 14 degrees, which falls perfectly into the standard healthy range of 8 to 20 degrees. Superheat proves the evaporator has successfully boiled off 100% of the liquid. This is the only mechanism that protects the compressor from fatal liquid slugging. Actual superheat tells you what the system currently has. But on fixed orifice systems, you have to determine the target superheat, what the system mathematically needs. This formula establishes target superheat. To solve it, technicians must measure both the indoor wet bulb and the outdoor dry bulb temperatures. The indoor wet bulb measurement is taken at the return air. This accounts for the combined heat and humidity load present inside the building. The outdoor dry bulb measurement is taken right as air enters the condenser outside. This dictates the total thermal load pushing against the exterior of the system. If we input an indoor wet bulb of 63 degrees and an outdoor dry bulb of 95 degrees, the math outputs a precise target superheat of 7 degrees. Fixed orifice systems require this dynamically calculated target because, unlike TXVs, they cannot physically adjust their own flow to compensate for shifting environmental loads. Diagnosing the state of the evaporator requires a direct comparison between the actual superheat you measured and the target superheat you calculated. If the actual superheat is higher than the target, the evaporator is starved. This indicates a low refrigerant charge, a restricted metering device, or a clogged filter dryer. If the actual superheat is lower than the target, the evaporator is overfed. You are looking at a system overcharge, poor airflow, or an overfeeding TXV. This establishes two rigid charging rules. Fixed orifice systems must be charged by superheat, while TXV systems must be charged by subcooling. Gauge pressures alone mean nothing until you do the work to convert them into actual saturation temperatures. You must map the physical states, run the saturation math, and let the thermodynamics reveal the true health of the system.